Hello, everybody. My name is Pete Kugler, and I'm an engineering lead at Bungie, a studio that I've called home for the last 6 years. Our studio is most recently known for our cooperative shared world space shooter called Destiny, and its sequel, Destiny 2, which I'll be referencing throughout the talk. Today, I'm going to be speaking on behalf of a group in our engine team that we call Collaboration. Our group has been focusing on building technologies to facilitate cross-discipline collaboration through relevant tooling, optimizations to our build pipeline, and general infrastructure improvements. This talk is going to cover a lot of material, and I've tried to squeeze it into 60 minutes. So if there's anything that you'd like me to drill deeper into that caught your attention during the talk, please feel free to reach out to me, either through email, which I provide at the end, or in person afterwards. Also, I do want to warn you that this talk does make some assumptions about your level of comfortability with asset pipelines, build systems, and Perforce. So with that said, if that doesn't scare you away, all right, then I hope you enjoy the talk. Now, before we dig into our work, I want to start with a quick summary of the challenges that we faced at the studio when we were shipping the initial release of Destiny 2. Destiny 2 is quite a large game with a universe that we are constantly expanding with product updates. And each Perforce branch that we create for release consists of about 4 terabytes of source and game assets in total. And in addition to working with a lot of data, we also have a fair amount of developers working together within the same branch on that source and data. You'll notice that in this chart, as we were actively working on the first release of Destiny 2, we had well over 200 engineers, artists, and designers concurrently building the game, and almost as many as 400 at times. That's quite a lot of workflows to coordinate in one place to bring the shipping product together. And in addition to creating product expansions, we're also shipping continuous updates for our fans, which includes special holiday events, like our recent Valentine's Day celebration we call Crimson Days. In this type of a development environment, the timing of releases is critical. So we prioritized the prevention of production pipeline risk through known but slow development processes, like a pre-commit build pipeline that we call the Gauntlet. If you had a chance to see my talk in 2016, where I talked about how we developed a pipeline for managing game stability, I shared why we put a pre-commit system in place at Bungie to begin with. Without it, you get into what we call the stability death spiral, where issues start masking other issues, and you just lose weeks trying to get out of that cycle and produce a testable build. The check-in latency caused by using a pre-commit system was certainly hard on us, but not being able to ship would have been a worse problem. But I do want to share how hard that check-in latency was on our engineering department. In the top chart, we have a view of our monthly check-in trends within our engineering org for the 21 months leading up to the initial Destiny 2 release. You'll notice that we would delay our engineering check-ins for 3+ hours on average to ensure that each change was meeting a high stability bar before ultimately submitting. The time delay comes from running every local code change through an extensive pre-commit build and testing system. The result then is a relatively conservative monthly check-in rate, as shown in the bottom chart. The trade-off here is that we prevent our engineers from submitting a production blocker, which runs the risk of delaying a time-sensitive live release, and burning hours of development time for hundreds of other developers. And I do want to call attention to an abnormal data point on the top right. There's been 2 studios that I've been at that have gone through what's called an audio apocalypse. If you've gone through your own audio apocalypse, we should grab some coffee or maybe a beer later and share some more stories. Now, back to this. Isolation into a branch while developing an in-progress feature seems like the obvious step to take here, as that would have allowed teams to have more freedom and safety in how they work, empowering them to take risks without fear of blocking production. But our software limitations prevented that. as we are limited in our ability to scale our infrastructure to support an influx of branches. We'd have to throw away work from parallel content changes since we couldn't merge our game data. And there would be a higher burden of managing integrations and new build system jobs put on the select few that have historically handled that process for the studio. So despite being aligned with small team development methodologies as an agile organization, we had technical limitations that prevented us from actually working the way that we intended to. And before I get too far, there's a couple terms I want to cover that are a bit overloaded. First one is feature branch. In the context of this talk, feature branch is a branch that has a temporary shelf life. It's created for teams to work on significant features together in without interfering with the stability of the main line. In a Git repository, it's pretty common to create feature branches at a much higher frequency than how we're creating them within our Perforce depot. And I also want to note that our feature branches are full branches. They are a complete lazy copy of all the source and game assets from the main line. And the second term is small team. So I'm talking about a small cross-discipline team working on shared features collaboratively. In some cases, like on the engine team, a small team is composed mostly of engineers and maybe a tester or two. But in the majority of the cases, like on our game team, a small team is a true cross-disciplinary team where you have maybe 1 to 2 engineers, 1 to 2 designers, a few artists, and whoever else is necessary for delivering on that feature. And yes, we're talking about small team in the agile sense of the word. I now want to share a fictional example. I'm going to say that a few times to illustrate how badly the collaboration process could get with our scale. Say you have a gameplay engineer that wants to introduce some cool new behaviors to our spider tank. Rather than having the tank, crawl around on 6 legs, we decide to have it sprout wings and fly. Due to technical limitations, though, the small team could not move out of the main line into their own feature branch. So their ability to take risks as a team was constrained. To get the change to her cross-discipline team, it has to go directly into the main line. So in our case study, our conscientious engineer goes through our pre-commit build system so they don't risk blocking production for the entire studio. They send their changes to get built and tested on what we call the gauntlet, and assuming her changes pass testing the first time, the changes will make it into the nightly build after about 3 hours, unless there's an audio apocalypse going on. However, the nightly build is not always what people are comfortable deploying, since content creators generally want some assurance that humans have done a test pass against the build first. That way they're not wasting their time deploying and launching faulty tools or a bunk version of the game that crashes. And waiting for a build that is approved by the test team could take over a week. And on average during full production on the initial release of Destiny 2, it was about 12 days. The delay was in part due to our QA team being thorough in their testing, supporting multiple releases, and also having to chase down hot fixes to apply to the build that aren't caught by automated testing. Each hot fix resulted in the need for a new build and a new set of tests to be run. And that's why ultimately it wasn't uncommon for this sign-off process to take close to 2 weeks to wrap up. Now I'll note that our support teams have worked really hard since Destiny 2 initially released to ensure that the nightly build does meet a higher quality bar for our content creators to consume. So what this all means is that despite being on the same team as a designer, there is potentially a 2-week turnaround time to deliver functional changes to enhance the gameplay experience for them. This discourages rapid changes from engineers who then feel that they have to get everything right on the first check-in. As you can imagine, working in this kind of environment can be a big morale hit, and also be a factor for having to say no to an innovative but deemed risky feature that they just don't have the proper time to iterate on. And so sadly, due to risk and time, we had to cut the wing spider take from Destiny 2 in this fictional example. And now you know where the saying, "when spider tanks fly," comes from. Huh? If you thought that joke was bad, don't worry, the rest are way worse. As the intro slide, as well as the case study hopefully demonstrated, we felt that having the ability to support feature branches for our small teams was really the next logical step for the studio. Going into this work, we started with a vision that has very much been a North Star for the collaboration team. First and foremost, with feature branches, teams should be able to work independently without destabilizing other teams. I think this is implicit by just being in your own branch. Second, rather than relying on pre-commit testing to hold the stability bar, we instead want to rely on background testing that is relevant to the small team. There should be less communication barriers in place, and with fewer people, it should be a lot easier to pinpoint and address errors. Third, we still wanted pre-commit testing to be utilized, but as a requirement for check-ins into the main line, and limited to changes that are integrating out of feature branches in the background, as nobody would be directly checking into main anymore. And by default, integrations would be one way into main, and they would be automatic. In main itself, we'd rely on the QA team to still run their weekly test pass, pushing the changes that they ultimately sign off on out to the other branches when they wrap up. This would get people safely in sync with other teams, but shouldn't be something that those teams need right away. Otherwise, they might be working within the wrong branch. And I'll note that we do have some branches where multiple teams are working together. And if that 1 week latency is a concern, small teams should be able to bypass that if they wish and just receive two-way automatic integrations for their branch. And additionally, if the QA team needs isolation from all these automatic integrations that are coming in, they should have the option of testing within a stabilization branch before performing their push. I'm proud to admit that our team was able to achieve this vision, but there were 3 challenges that we had to overcome to make attaining it a reality. First, we had to make some core changes to our infrastructure to handle the new scale that we would incur from going from one main development branch per release to a release that supported many small team feature branches. Second, we needed to make the migration into feature branches a seamless experience for content creators. It would be a non-starter if work was to be lost, so we focused on the ability to semantically merge content. And third, we had to make it as simple as possible to move the changes around our ecosystem without introducing global instability. We developed automated systems to safely integrate changes with as few interruptions as possible and gave people the tools that they needed to manage that flow. Now let's dig into the first challenge that we tackled, scaling. From a source control management perspective, what we wanted with the small team development vision is not too out of the ordinary. We knew that there are some commercial solutions out there that solve some of the problems that we were tasked with building, like Perforce Streams, modern technology that's built around smart branching patterns. Last year, Paul Hale gave a really nice talk on the Call of Duty shipping pipeline that's worth watching. And you'll also pick up some tips on some best practices to use with this technology. Ultimately, though, there were a few cards that were stacked against us that made the migration to that technology difficult for Destiny. People had grown accustomed to mapping in multiple branches into their workspace for the staggered releases that they were working out of. And they built the expectation, theoretical or not, that they should have immediate access to anything that they have mapped in. And also, our branches are rather large in size. As we check in our source assets right alongside the game data within the same folder, no less, which you shouldn't do, by the way. By source assets, articulate, Pete, articulate. I'm referring to files generated by digital content creation tools such as Maya and 3ds Max. To keep our sync costs low, we have custom file mappings for varying disciplines on the floor, as most people don't need to map in these particular file types. We'd have to map paths out at the scope of the folder rather than the files if we were to move to streams, which would require us to perform a large reorganization of our content and the references to it. And lastly, as brought up in the intro slide, we are a live game that is continuously being patched with time-sensitive releases. Changing the depot over to a stream-based one during active production was a risk factor in the project that we weren't comfortable taking on. So we made some compromises. We've updated our processes and tools to behave like streams where possible. It does mean that there was a bit of reinventing the wheel, but that ended up being just a fraction of the ultimate work that we did to support this development ecosystem. And second, we know enough from our evaluation to make an easy sell to set ourselves up for a stream-based depot on future projects where we have a starting point that carries less risk. One of the wheels that we had to reinvent was setting up a source of centralized branch authority, something you get for free within a stream-based depot. Now, admittedly, we have some old code that we aren't proud of, where we had some hard-coded lists for defining branches, or crawled the entire depot parsing XML files to extract branching information for our tools. This made it quite the ordeal anytime that we wanted to introduce new branches to Destiny, as we'd have to consult with a variety of teams to ensure that the branch was being properly registered in their respective tool or system. And while it's not groundbreaking, what we did here was create a table on our build farm that served as the authoritative source for everything about our branches. Each branch is a foreign key into a project and release table. And so in this example entry, project is Destiny, the release is V210, the branch is named Sandbox. And kind of the cool thing about having this flexibility is that we can then utilize a branch name across various releases. Just think, I don't know, sometimes you get tired of coming up with branch names. Also, these various tables allowed us to have settings that were established at a global scope to everything within a project or release. A practical example of this is with our build definitions. There are certain build jobs, like that of our content creator tools, that we want to have active across all Destiny branches. We can now define that definition at the scope of the project and have it automatically applied to all releases and branches ever associated with that project. The next obstacle to tackle was getting an indefinite number of branches to fit onto our build machines. Our original process did not lend itself well to that goal, and I want to talk about that a bit, and it did require some revisiting. Earlier in Destiny's project lifecycle, when the branch count was easier to manage, we'd simply edit the Perforce workspaces directly to map the new branches onto our build system infrastructure. We had a nice tool to simplify the process, allowing us to update many machines at once. In this process, each branch would get mapped into its own unique folder named after the branch being D2 Warmind in this specific example. Eventually, though, we began growing the number of branches that we were required to have mapped onto our build infrastructure to support our new releases. Since the releases were all similar in their respective layout, we were able to lean on the Windows Server NTFS deduplication service to keep our large branches from blowing up the servers as we enlisted new ones. The process then of adding a new branch to our build system required that we include a step that interweaved syncs split by subpaths with calls to enable and disable the deduplication service on each machine. With this process, it took about 2 weeks to get a new branch mapped and usable across the entire build system. But unlike fine wine, time does not make this a delicious experience. Like I said, I tell terrible jokes, but thanks for laughing anyways. As you could imagine, the process was way too slow for production expectations. And we needed to establish an automated way to dynamically handle new branches as they were created. To support this flow and provide a branch to a team that was immediately usable upon creation, we had to establish a dynamic system for how Perforce client workspaces would be managed on our build farm. If we recall from the previous slide, we used to map depot paths to a folder named after the branch. Now, rather than treating all the folders that we map to as distinct branches, we decided to instead map to a folder with a more abstract name that we could share across branches, called a slot. In this example, rather than mapping the D2 Warmind branch to a D2 Warmind folder, we are mapping it to a slot folder named D2_00. This slot folder represents a container for any branch that shares a logical grouping. That grouping would naturally be branches that are part of the same project, like Destiny 2. When we assign work out to our machines on the build farm for a given branch, we prioritize finding machines that have that branch already mapped to a slot. However, if one can't be found, we simply find a machine that has another branch from that logical grouping mapped. To reduce the sync delta, we're currently working on having the assignment logic sort on the file count difference between the branches from information that's pre-computed. That way the machine assignment can remain fast. Once a machine is assigned, if needed, we change the depot mapping to reflect the new branch that we want to put on the machine within that slot folder. The client mapping to the folder remains the same, only the depot path changes, as in this example, where you're changing the depot path from D2 Warmind to D2 Forsaken. Then before starting the work, we sync using the local paths. Using the local paths for the sync is absolutely essential if we don't want to leave out files that were added or removed in the target branch that we're swapping to. The sync will pull over the deltas between the two branches and update the have table with the new state. However, there is some overhead with the have table update that we've noticed. Even in the case where there's no differences between the branches, it still took about 10 seconds for a swap between our source code and about a minute for our content. If we were using a stream-based depot, rather than performing a slot update with this custom tech, we'd instead perform a workspace swap, which in theory should avoid this overhead, but it's not something that we had a chance to measure in full production since we didn't move over to streams. And if we wanted to reduce the odds of experiencing swap overhead, we have the ability to configure the machines to hold a higher slot count for a given logical grouping. So in this example, we have 2 slots for the D2 grouping with folders named D200 and D201. The trade-off with increasing the slot count is that a machine can fall behind on its sync state if the slot has been unused for a while. Currently on Destiny, mapping 1 to 2 slots per machine has been our optimal sweet spot. And now to shift over to the changes that we had to make to our asset pipeline. This picture's so cheesy, but I love it. Similar to systems that other studios utilize, we have a cache for our intermediate game data that we seed from the nightly builds produced from the build farm. This is used to allow people to skip the process of baking assets that they have not made local edits to, as they can simply download those files instead. For a deep dive into Bungie's asset pipeline, I'd recommend viewing Brendan Morrow's talk from last year, which includes an overview of how the remote game data cache that I'm about to talk to fits into our content system as a whole. Now, similar to the initial limitations that we had with the build farm, there was a physical limit to our ability to scale the system to a dynamic branching model. In the original system, we typically dedicated 1 machine as a storage cache for an entire branch. And in some cases, it would act as a storage cache for 2 branches. In addition to acting as a storage cache, the machine also hosted the service that is used to interface with the cache. To give you an idea of what this service does, it helps to understand how it fits into the flow of the nightly asset bake and packaging build, which I'm just going to refer to as a content build. Our content builds are best described as IncrediBuild for game data, or SNDBS, depending on what kind of shop you are. We have a controller process and a set of follower processes that coordinate with the controller to read and write to that remote storage cache. One dedicated server is chosen as that storage cache for the entirety of the build. And a service hosted on that same machine is used to build up the index into that cache data and guard against race conditions from the multiple followers. This requires that the service remains stateful and that it is always live, as bringing it down for any reason, even maintenance, introduces a halt to the content production pipeline. Fortunately, the system architecture made it impossible to scale to our vision without ongoing hardware and manual setup coordination. This is because each new branch required potentially standing up a new machine, a service deployment, and several other manual setup steps. To effectively scale the service to handle dynamic branches, we had to address 2 core areas. First, we decoupled our storage from the service and moved it onto dedicated hardware to hold the data for all branches. The data is now organized in a branch-agnostic manner, residing behind a unique alphanumeric path based on the checksum of the data contents. This allows us to more efficiently hold all this data, as it avoids storing duplicate data across machines as we were previously, since many branches actually produce the same intermediate output. Second, we made the service stateless so that it could handle requests for any branch concurrently across a pool of machines. This meant that we no longer were tied to setting up a new machine to host an instance of the service for each branch that we wanted to introduce to the ecosystem. To do this, we had to move our state and lock management into Redis, which is a fast distributed in-memory key value store, and we moved our logging out of the local file system and into Elasticsearch, a distributed big data search engine that made it easier to aggregate our service logging that was now being distributed across multiple machines per content build. These changes then allowed us to move the service behind a commercial load balancer, enabling us to add more hardware when the load increased, rather than having to do so simply based off of when we wanted to introduce new branches. So at this point, we almost have all the pieces necessary to dynamically add a branch to our infrastructure. We have a central point of branch authority for tools and services to be aware of a branch. We have the ability for a branch to be mapped to a build machine automatically as soon as a machine for that branch is needed. And we have a game data cache that can be shared with other branches without requiring any manual setup work. The final steps are to, well, add the branch. You don't have to laugh at this one. It's awful. We joke that it can all be done with the push of a button, but really, it's a command line we call. Also a dumb picture, sorry. This command starts by simply calling the perforce populate command, which is broken apart by subpaths to reduce impacting partners that we may need to replicate our perforce data to. We then register the branch with the build farm database, or source of truth. And now, after about 5 to 10 minutes, a lazy copy of the 4 terabyte branch is created. Everything is live on the build farm and within everyone's local tools. At this point, people can kick off builds and immediately sync and work out of the new branch. I'll note, yes, our branches are big, and we've been working on reducing the size of them. We've cut it by 11% recently. It's also worth noting that we only utilize 23 terabytes on the back end for all our products, as we aggressively obliterate unnecessary files and we don't check in build system artifacts. While it was a big accomplishment that we can now quickly create and support an indefinite number of branches, we wouldn't be able to take advantage of that work if we couldn't move content creators into those branches to begin with. To do so, we needed the ability to safely merge their game data as a prerequisite. I'll now go into what we did to remove those barriers to entry. Our game data file type supports a text-based representation. But as you can see from this picture, the raw data structures that the file encapsulates do not merge cleanly line by line. If we did have the expectation for our content creators to manually merge this data within a text merge application, we'd be requiring that they understand the underlying data structures and programming language semantics associated with the file format. This might be reasonable with simple structures, but our game data also supports arrays, pointers, polymorphic types, which would make merging content in this manner a frustrating feat that is both time-consuming and risky. And by encouraging teams to now move into feature-focused branches, we're introducing the risk of having a higher volume of unmergeable game data get developed in parallel, which brings up 2 challenges in particular. First, since we couldn't merge the game data line by line like we can with our source code, well, then we'd had to historically then, in those cases, well, we would just treat every merge attempt as a conflict. And historically, since we didn't have an intuitive way to interactively resolve the conflicts, the general practice was to either accept one change or the other, and then manually redo the lost work. Pretty shitty workflow. Now, we could safeguard against having to redo work when everyone was working within the same branch. We'd simply mark the file as exclusive, which implicitly enforces through Perforce that only one person at a time can edit the file. But that takes us to our second challenge, in that we lose that lock protection as soon as we allow for people to work on the same data across different branches. So what do we do then? We had to build a system to merge the data structures themselves with code that is aware of the language semantics that they're built on top of. From the start, we knew that it would be an impossible feat to handle automatic merging for all the content in our game, especially given the flexibility that we allow engineers to have with the creation of our game data structures, and just the plain fact that designers are going to naturally work on overlapping data fields. So we targeted an 80% automatic merge rate, and knowing that we weren't going to hit 100%, we built the system to be extensible and debuggable. This is the joke that only C++ developers laugh at. Everyone's a C# developer in here, I guess. I am too. To achieve our extensibility goal, we chose C# as our core language for the system, which made it easier to interface with our C#-based tools, and it allowed those not as familiar with the game engine to participate in extending it. To evaluate our success rate, we performed targeted instrumentation that allowed us to view our automatic resolve to conflict ratio as our code was running in production. Additionally, each merge operation created an HTML report to provide us with visibility into the work that the merge code performed to make sure that it was operating correctly. And if we did hit an issue in production that we either should have been able to resolve or resolved incorrectly, we had the ability to then recreate any of those integrations so that we can test them against our code. This was also invaluable during early development when we were trying to figure out the best way to solve some of our historically complex merging scenarios. And lastly, we built the system from the start against a test framework, where we artificially created as many new scenarios that we thought that we should support, and then gradually introduced new ones as development progressed and new cases were uncovered. Now, before we get into the implementation details, I want to cover just a few terms that I'm going to be using throughout the next few slides. The first term is source. This is the incoming change in an integration that collides with a pre-existing change. This is often referred to as the left change. The second term is the target. This is a pre-existing change that collides with the incoming change. This is interchangeably referred to as the right change. And then we have the base, which contains the closest common ancestor between the source and target changes. You'll oftentimes hear the base change referred to as the original change. And you'll oftentimes be reminded of this meme as well when you're working on this technology. Our game data structures that we serialize to content files are authoritatively defined in C++, as in this simple example with the Jetpack game data structure. Now let's take a look at what a merge would look like to this data structure. At the most basic level, our merge algorithm consists of just enumerating through the internal fields of the data structure and performing the following test. If the source is the same as the target, just take the target. If the source is the same as the base, we take the target as well, since that is a newer change. And if the target is the same as the base, well, we instead take the source, as it is now the most recent change. And if neither the target nor the source match the base, we raise a conflict for this particular field. If any of the fields within the structure have a conflict, then we mark the entire structure as having a conflict. As you could guess, most of our game data structures are not that basic. Using the strategy design pattern, we have developed several different types of algorithms that we call merge providers to handle the complex data structures that we support in our game. These algorithms are paired with the data based off of their game data type. Within these complex data structures, the merge code enumerates through each of the data structure's fields, utilizing the appropriate merge provider for each field. In some cases, we have merge providers that call into other merge providers as necessary until we're able to drill down and perform the basic primitive field merge that we covered on the previous slide. A simple case to start with is our merge provider for merging static arrays. A static array is your typical array, depending on what language you work in, that is fixed in length and each of its elements are of the same data type. Our algorithm consists of traversing the source, target, and base arrays in order from the first index down to the last and performing a horizontal merge one element at a time. If any of our elements in the array have a conflict, then we consider the entire array to be in a conflict state. Now, the dynamic array is a more interesting case. A dynamic array varies in its length. And because elements can be inserted and deleted at varying locations, we can't rely on an integer index for performing a horizontal merge, as we could with the static array merging. So instead, we need to create our own key for traversing and accessing the elements within the arrays. An example of using a dynamic array in our content is with our scene editor. In this example, our scene has 3 nodes contained within a dynamic array. We have a start node, an action node where the actor is casting a spell, and then the end node. If I wanted to add more nodes, I can grow the array to insert them as needed. So in this case, for dramatic effect, I'm going to add a 5-second sleep right after I cast that spell and grow the dynamic array by 1 element. When selecting the array key, we use the first string field value in the structure by default, which would be the value assigned to the scene type in our example here. This tends to work pretty well for the majority of our game data types. We fall back to the first primitive value if a string can't be found. So now in this example, I stripped out the scene type, so we no longer have a string to work with to use as a key. We must instead rely on the ID, which is still a completely reasonable choice here. And additionally, we can customize our key creation logic by using C++ data markup that we can use to inform the merging API how to generate the key. You can base a key off of a field name, a field type, a field value, type of a pointer, or even a combination of things. Our merge algorithm then starts by querying the keys from our 3 input sources, that being the source, target, and base array that we are attempting to merge. And if we identify that we have duplicate keys, we append serial numbers to each duplicate instance, starting at 000. We then enumerate through the keys and merge each element. And if we happen to come across a case where the base and target element are missing a key, then we consider this to be an add operation to the array. And we pull the source into the merged result. And when the base element is not missing a key, but the target still is, then we consider the operation to be a delete, and we remove the element. This insertion and deletion logic here is a similar but slight variation to the primitive merge logic algorithm shared in the earlier slide. And throughout development, we encountered many other interesting cases that we've built special purpose merge algorithms to handle. This includes the ability to merge polymorphic pointers. A practical example of this case is with our timeline editor, where timeline is represented as an array of polymorphic pointers that can dynamically switch their types based off of user intentions. For this algorithm, we attempt to merge the pointer type to resolve the structures that we're pointing to, and then we merge the data from the base and derived types. And we also have a way to handle timestamps that certain tools fix to the data. In this case, we just take the newest timestamp. Another special case is for merging our part labels, which is a system for tagging content. For this case, we just perform a set union to join together the content tags. And as you can see, we have quite a few more. And in addition to performing merges to our data based off of the game data type, we also have a few tricky edge cases that we have to handle as well. These special cases are identified based off of C++ attributes applied to our game data structures. One of the most common edge cases is that of the atomic structure. An atomic structure is a structure that doesn't support per-field merging. A perfect example of this is a 3-dimensional vertex. Typically, when a vertex is created, its positional information is created and placed as a whole unit. There'd be some rather strange bugs observed in the game if we were only to perform a merge on a subset of its dimensional fields. So in this case, if we detect that any field has a merge applied to it, then we treat the entire structure as having a conflict, forcing the user to either take the source or target vertex in its entirety. Another edge case involves handling the precision of fields marked with comparison epsilons. A practical example of this is with our data structures that contain vertices that we perform chain transformations with before we serialize them to disk within our editors. As long as the precision of the fields that we're comparing against fall within a reasonable range, we shouldn't force an unnecessary merge. Otherwise, we'd get a lot of noisy atomic merge conflicts to deal with when trivial changes are made to the data. And the last case includes an attribute we have that just allows our merging API to ignore conflicts altogether, causing it to always take the target change. A practical example of this is with our shader editor, which saves information that doesn't affect the structure of the data, just the design data representing the position of the nodes within the editor. As this graph shows, since putting this into production, we've so far been able to automatically merge 80% of the data from our integrations. However, we still need a reasonable way to deal with the remaining 20%, which are reported as conflicts here, as we've come too far to still have to ask content creators to throw away and redo their work, because that is shitty. Sorry. We felt that people should and could be able to manually resolve most conflicts if they have a proper view on top of that result. So we built a content merging tool, which is pictured here to help with that. The tool is an interactive view on the data model from the merging API. The tool allows users to select values that they feel are logical for the merge before committing them to disk. And in this view, the tool is showing the interactive view users would take to address per-field conflicts. And in the cases where the view of the data is difficult to understand, they're able to open a read-only view of the data in the respective editor typically used for editing that data. A change they then make within the merge tool is reflected in the designer view that they are most accustomed to working within. Now, with the ability to merge content, we remove the obstacle preventing content creators from moving into small team feature branches. The remaining problem in front of us was how we would be able to safely move these changes around the branches without introducing instability to other teams, and without making the integrations become a cumbersome process to manage. The goal of moving teams into feature branches from the beginning was to allow small teams to work the way that they wish to work. And to empower small teams to truly own their working environment, we created a tool for helping them manage it called TeamSync. TeamSync starts up with a dashboard providing a curated view of their branch state. This includes active bugs in the branch, recent check-ins, and scheduled farm builds that have finished or are actively running against their branch. Additionally, they have the ability to schedule new types of build farm jobs that their small team is interested in having. This can range from running automated tests to managing integrations, or even doing cool things like running an automatic installation of their build to a given playtest lab. Lastly, this tool provides a safe mechanism for teams to pull in change lists along with dependent changes into their branch from another. I'm glossing the surface and hope that you had the chance or take the chance on the Vault to view my colleague Irina's talk on tooling for small team workflows, which covers this in more depth. The usual pattern that we're observing with the scheduling is that when a successful post-commit build finishes within a team's branch, that they're then chaining it with an automatic integration into the main line. The success of moving teams into their own branches relies on many integrations running successfully and silently while work within small team feature branches goes on uninterrupted. And it's worth noting that all integrations are gated by pre-commit testing to ensure that their integrations aren't interrupting other branches as well. The target branch for any integration, in this case the main line, defines the type of test suite that should be run before changes can be submitted. This includes the configurations to compile, the test assets to cook, and the test cases to execute. The first step in this automated integration involves reserving a farm machine from the build farm that is dedicated to the entire integration. It is synced down to the state where we can build and test the game. Once that wraps up, the integration is started on the machine. When we perform the automatic integration, we attempt to resolve what we can without user intervention. Usually this works just fine, but sometimes a person needs to resolve conflicts that we couldn't deal with through automation. We have an algorithm that attempts to find the last person from the branch responsible for the conflicting files. and we send them an email that they can launch Perforce's visual tool from to interactively resolve the issues that were found on the remote farm machine with an enlistment that is temporarily shared out to them. And if there were any content conflicts detected, then a similar link is also provided to a remote build of the merge tool, which also resides on the farm machine. And I'll note that the conflict assignment is not perfect, which is why we also provide an interface for users to reassign conflicts to someone that's more appropriate when those particular cases are encountered. After the conflicts are addressed on the user machines, the automatic integration then proceeds to the testing phase. In this phase, the farm machine that performed the integration is then used as a read-only file system for remote testing. Our build farm has the ability to execute tasks under different hosting environments. This includes the ability to run build tasks against a local test environment, an environment with a full Perforce enlistment, and a read-only environment. In the read-only environment, we are running our operations within the scope of a temporary folder with no enlistment. And because the work is performed in a temporary folder, local writes are allowed, and the files and folders that are read-only are symlinked in from the remote farm machine that was reserved for the integration. Certain paths are selectively linked in through a combination of file and folder links, as there is generated data that is produced adjacent to the source that we want to create within the scope of the local temporary folder. We also explored the idea of having all our build artifacts get redirected to a siloed folder, which would remove the need for this linking pattern, but worried a bit about playing a constant game of whack-a-mole, fixing up the varying ways that people set up their build projects. But it's something that we're considering to revisit as long as we have a procedural way to enforce it. During the integration pre-commit testing phase, it's not unusual for a break of some sort to get detected. If one is detected, we send an email to the relevant party whose changes we are attempting to integrate and test. They are then given instructions to log into the farm machine that is performing the integration and fix the issues from the report. When they log in, they'll notice that the intermediate file caches for the binary build and asset banks are already warm. This is because we run a local version of part of the pre-commit build on the integration machine while the remote one is running against its file system. All of the standard development tools that our engineers are used to are installed on the machine to minimize the context switch from going into a separate environment to fix up the breaks. Once they've fixed the issues, they simply click a batch script on the desktop to re-kick the remote pre-commit job. If everything passes, then the integrated changes, any conflict resolves, and any fixes that were made on the machine will get committed to the depot. You don't want to see me dab. I was thinking about it. Next slide. This integration and testing workflow was the first time that we've allowed users to log into a farm machine while it is running work and give them the ability to perform modifications to the file system. This introduces a high risk of putting the build machine into an unreliable state for future tasks. To ensure that we always leave the machine in a clean state, we created post-task operations. Before a client task starts, we queue up a definition for our post-task operations into a database table. And after the task completes, the post-task operations are pulled from the database and executed on the machine before any new work is assigned to that machine. Examples of some of these operations include fixing up any file state discrepancies detected within the Windows file journal, restoring any permission changes, such as the workspace sharing that we perform for the conflict emails, and reverting any files with pending edits. If any of these post-task operations fail to run, it's critical enough that we have the machine automatically disabled until it can be manually recovered and the issue codified around for increased robustness. With this tooling and robust automated system in place, we feel that we've built an ecosystem that achieves the goal of empowering teams to work independently and keep their branches in sync with minimal overhead to the team. And now, to share where we are now with all this tech. On the Destiny Engine team, we break big bones and reset them to make substantial leaps with our technology. Being a live game, it's important that we don't cause a noticeable amount of disruption to the production cycle. That's why we bring our work closer into the shipping releases as our technology becomes mature, and when the risks are deemed to be low or the benefits outweigh the risks. The following charts show where we are with the adoption of the technology that I've covered today. Each branch and project across the studio is using the Central Branch Authority updates, and this has been in production for well over 2 years. The dynamic branch swapping technology on the build farm has also been in production for over 2 years, with usage on 82% of the branches that we build from in the studio across multiple projects. The branch-agnostic game data cache carries a bit more risk, so despite also having a long production shelf life, it's currently in use for 63% of our Destiny branches. It's not a technology that we've used on any of our shipping releases just yet. Our automatic content merging, despite also carrying a fair amount of risk, has provided such a time savings from not having to throw away and redo lost work that it is being used across 92% of our Destiny branches. And as you can see from this chart, there has been almost 70 unique users, some of which are performing a staggering amount of merges. These people are more than likely responsible for integrations on their teams and are probably going to really appreciate the automatic integration tech. And then the last bit of technology we shared with the automatic integration tech is something that is rather young, but I'll note that we're on the 4th and final version of it. While we talk about Audio Apocalypse, I can talk about why we're on the 4th version of this. 76% of our branches across all projects that we build utilize this latest automated workflow, and we've observed over 300 and counting successful end-to-end integrations with this technology. And from a holistic view, I have a few charts to share that compare the development patterns between those that are working in the traditional Destiny branch model that we shipped our initial Destiny 2 release from versus our small team feature branch ecosystem. First, we have a chart to visualize the delivery time for a change in the mainline branch that we shipped the initial Destiny 2 release out of compared to that time within the small team feature branch ecosystem. The chart is using a logarithmic scale to make it easier to view the differences between the build times. And I want to note that for each column here, that we're viewing the best average cases, so no Audio Apocalypse. In addition to the fact that we are now compiling code at half the time and cooking assets at a quarter of the time with incremental patches, and this is all due to being able to basically be able to work in an independent branch to break bones to make those kind of changes, we've removed the need for the lockstep 12-day QA sign-off process, yet still have the ability to get a build that is stable and safe to use with changes from an engineer to their team. And not only does working within feature branches increase the rate at which a small team member can consume an engineer's change, it also creates an environment where engineers are able to iterate at a faster pace, as exemplified in this view on our average engineering check-in velocity rate per month, where we are comparing check-in rates over 21 months in the small team feature branches to the check-in rate in our Destiny 2 mainline branch within the 21 months leading up to its initial release. So the bottom chart is the one that I showed earlier on the intro slide. So this is awesome. To wrap up, it's only fitting that we return to our fictional spider tank collaboration example. As you might recall, we had to cut the fictional flying spider tank feature due to the time it took and the ship risk associated with the change. Now we're in a different development environment and can take another stab at this. And we'll do so by now introducing a sharp stabbing stinger to the spider tank. First, before we begin our work, we'll create a new branch based off of main called the sandbox branch. We'll base the creation of the branch off of a stable test pass that the QA team ran in main. Once we move the small team into the branch, the engineer and the team begins their work and checks in their change immediately, as there's no risk that her change is going to break other teams. And if it does break the build, it's only blocking the pipeline for a small group of people. The designer then waits about 75 minutes for the change to get built and automatically tested, which provides enough confidence that the change is safe to sync, or a fraction of that time if they wish to skip the stability checks. And I'll note that it's going to get even faster in the near future, which is awesome. And when the team is ready for the change to go out to the other branches, they will turn on their automatic integrations into the main line through Arena's branch management tool, TeamSync. And know that the QA team will only push out the changes to the other teams if they're deemed safe to publish after going through their extensive test pass. With this work, I feel now that the goal of achieving a small team development environment at Bungie is complete. Not only do we have the team rituals in place that we have internalized over recent years, we have an environment that is set up to provide an equivalent development experience where people can learn from their mistakes and have the freedom to make technical failures safely as a team and continuously learn and grow from the experience. I'm really excited to see the innovation as a result in the years to come. And there's a lot of people to thank for this work in both advocating for it and providing technical help and feedback. This includes our build verification team, the IT team, the Perforce administrators, the infrastructure team, our production engineers, and many more kind and hard-working folks across the studio. I also want to thank Jeff Evans for his mentorship in preparing for this talk, and Stan Spivakov, who actually planted the seed that resulted in this work. And Joseph Mortensen, who was my first intern that I've managed, and the one that worked with our team on the farm workspace technology. And of course, the collaboration team, whose work I am lucky enough to speak to today. And yeah, thank you for attending. That's it. So, I think you guys have like an entire 4 minutes to ask me questions, but I'm could meet afterwards as well. And please feel free to email me.
Hello.
Hi. I think you. All right, go for it.
Here. Thanks for the talk.
No problem.
I had a question regarding the merging process.
Sure.
So when the small team had to merge from the main branch into the feature branch, this was done automatically, but 20% of the time there was actually conflicts. So did the team itself merge those conflicts every week? And if so, how much time did it take for them to merge those conflicts?
So that's a good question. So initially, in those cases, the 20%, kind of in the old world, before we introduced the merge tool into the integration pipeline, we went through the old process of basically take one side or the other, redo the work. But then once we were able to get the merge tool as part of the process, then they would just open that up in the email and then just go through the fields, take what they wanted, close it, it would commit to disk, and they'd be on their way. Does that answer your question?
So it was pretty quick for them with the email to.
Oh yeah, it's really nice. Yeah, they're in and out. They don't even have to worry about much of a context switch. They just click the link, it opens up the remote build that is schema compatible, and yeah, it's good to go. And the experience that actually, well, that's cool, man. The creation of the merge tool itself is like worth a talk. Like the kind of the main designer for it, James Haywood, he went through a lot of iteration with the UX team. Actually, there's a talk that'll probably be in the vault from Caroline Cologne that goes through some of the UX process that went into building the merge tool. A lot of it was prototyped with paper first, because that's one of those tools where like, I think handling a conflict is just, it's not a pleasurable experience. You just want to be fast. You want to get it done and be on your way. And so how do you make a pleasurable experience for something like that and ask content creators to do it? That's a huge challenge. And so they went through quite a bit of paper and pencil iteration to make that happen. But I think they achieved it pretty well. And then, of course, because it is a view on our raw data, it's not always a pleasant thing to work with. So that's why that extra work that Arena hooked in that basically opens up a read-only view in the relevant editor, it just is icing on the cake, and I think handles the corner cases where it looks a bit awkward in the merge tool. So, I answer anything for you?
Yeah, it does. I have a quick question.
Sure.
When merging back into the main branch, did you have a lot of race condition of several feature branches touching the same files, trying to merge back into the main and having conflicts with each other?
What'll happen in that case is if we do end up hitting a race condition, then one submits first, checks in, and then the other one will essentially have to kind of start back over. So the whole integration process, it's running through a state machine, and so then it just goes earlier on in the state machine and goes back to the start where it's like, okay, we found some kind of overlapping change. We need to go and kind of resync to the head of the target branch, and now we need to go and perform a resolve again. Oh, we found some conflicts. Okay, send out the mails to the relevant parties, and kind of just goes through everything again. But that's how we deal with that. It's worked fine for us. I think we found that there's not too many folks that have hit that kind of scenario. We tend to send about between 1 to 3 integrations into the main line from the feature branches a day. And right now, we have 10 of these feature branches going, and it's been going on for almost 2 years. So yeah, it's been all right.
Thank you.
You're welcome.
Hi.
Yeah.
Every tool that you talked about today was created by Bungie, or you use like third-party open source or something to base it on?
Oh, no, we're nuts. We built all that in-house. Yeah. Yeah, I'm sure that we were inspired by other things that are out there in the industry for sure. Yeah, all that tech for the internal tools that I showed pictures from were developed by Bungie engineers.
How long it took to create all those artifacts, all these tools for you to use it?
Oh, I don't know. Years and years and years. And, you know, there's been different variations of things, and they've had different names and built different technologies, and everything is an iterative process. And so, you know, there's like an initial version of something that goes out, and then that inspires some new ideas, and they make improvements to that, and becomes something new. And then that, you know, then people get new ideas, or they go to GDC talks and get inspired by some of what they see from others in the industry, and they come back to the studio and they go and do some new stuff to the tools that are there. So we're constantly just evolving what we have. So I mean, it's some of our tools have been around since Halo, and we've just continuously evolved them to, you know, be something that works with Destiny.
Okay, thank you.
Sorry, it's not a precise number, but okay.
Hi there.
Yeah.
I noticed perhaps a lot of your problems might have been solved a little bit easier if you were using Perforce streams. Was there a reason you didn't adopt them earlier?
Oh, I think that I don't know the historical context behind that. I know that there was an evaluation that was done earlier during Destiny 1 that didn't go so well, but I wasn't a part of that, so I'm not sure why that went south.
Okay. And just
But I think that was one of the reasons why we were a bit kind of, I guess maybe a bit nervous about doing it now, that we thought like, well, it didn't go so well in the past, and now we're in active production, and there's time-sensitive releases, and I don't know, kind of scared to try this again, because maybe we'll hit the same problems before, even though people said everything works, and yeah. But yeah, unfortunately, I don't know the historical context, though, for why that happened, or why I said no the initial time.
Okay.
But that's a good question.
One other quick question. So how many concurrent small team feature branches would you have running at any given time?
I think right now, I believe we have 10 going.
Right.
Yeah.
Thank you.
You're welcome. And that's per release, and so then what'll happen is as you have new releases, there may be another subset of feature branches depending on who's assigned to that release. Yeah.
What's the average scale of your feature branches? Would you do them for your example of the spider tank with like a small feature like that, or would it scale up to, say, a branch for a particular content release?
So what'll happen is, that's a good question. So when there's a point where we're about to, you know, release something, is it time? 2 minutes? Okay. What'll happen is we'll eventually, as we get closer to, you know, needing to ship that release, like as we're getting to, you know, past the, getting closer to ZBB, what'll happen is we'll just start to collapse into the main line, and then we'll go back to mainline development, and then people that are doing kind of the forward-facing stuff will then be in feature branches on, you know, based off of later releases. And so then we would always ship out of the main line and not out of one of the feature branches.
Okay, thanks.
Hi, thanks for sharing. I have a question about content merging. How do you merge the binary files like texture or audio files? Do you have a mechanism to prevent people edit these files at the same time?
That's a good question. So no, we don't merge audio files, but what we did for that is we actually, I have like 60 minutes of stuff I ripped out of this. One of it was about this particular topic. So we ended up creating kind of a sibling set of branches, and we're able to utilize ditto mapping to perform a one-to-many mapping of the source data, you know, the audio files into the different branches that you might have mapped in. And so ditto mapping, basically the way that works is the first entry you have mapped in, you can edit, but then all the subsequent ones are read-only. And so then we have to manage like being able to like, if I go from whatever Forsaken to Warmind, I need to go and kind of change what is ditto mapped so I can, you know, edit the stuff alongside my game data. Is that answer your question?
Yeah.
Okay. Unfortunately, we weren't able to do that with some of our other, DCC source. Okay. Yeah. But it'd be cool if we could do that with some of our other source data, maybe someday. But we find that that doesn't tend to overlap that much.
Okay, thank you.
Okay, all right, thank you very much.